Hello, my fellow aspiring engineers. It's good to see you here. My name is Paul Ang. I'm coming from AMD Singapore as a IC design engineer, specifically in the physical design domain. Today, I'm going to share with you the introductions of IC design process because recently I'm being tasked to give an overview of this to the interns that just joining us. So I just thought of why not I just record a video so that it can benefit um, the intern that will be joining us as well in future, and also I hope also able to benefit you because you might be just graduated or probably you will be graduating soon. So by going through this video, I hope that you can get a more clarity on what we do as a IC designer, and also what exactly is the flow itself. Then from knowing all this detail, you could probably make a better decision to see whether this industry, whether is it good for you and whether you want to join it. Alright, and today I'm going to explain the overview with a metaphor of designing a building, because I feel designing a building is some sort of kind of similar with IC design. Okay, so let's go straight into the details. Let's start off with specifications. So you could have your market, you could have your customer. Definitely both of them will come with some sort of demand. Let's say you are targeting your gamer community. Definitely they are looking for high performance, and power might not be an issue for them because they normally just put the CPU in the desktop. So desktop you just plug in to the power socket and there's no battery issue. Okay, or probably if let's say you are targeting a gamer who like portability, he's looking for a laptop with ultrabook features, then definitely that will make the area of the chip become an important role. That it will make it smaller, power efficient, so that they can bring the ultrabook to any way they want to use it. Okay, and let's say you target another community that aerospace. Okay, for example, SpaceX or NASA, they are using the Xilinx chips to go to the space itself. Definitely the durability of the robustness of the chip is very important. It's supposed to be designed in a way that it's able to sustain a long service time in the space. Alright, so they need to undergo probably a very robust design so that it will not have any faulty issue on the space itself. Alright, so that could be another specification. Okay, and all this specification is important because it once it's defined, then they were being passed to the architecture team to decide the further details item. In the context of designing a building, the specification itself probably means whether like this time the developer want to build for a luxury design or not. Are we targeting the middle class? Are we targeting the higher earner? And this time around, whether the land bank that's being given, whether is it we can build landed property or we can build condo. Okay, all these kind of different specifications. There's something that's more details, yeah, but I'm not going to it. But this is the specification that it needs to be researched from the market demand, and then from here we're going to form the specification and pass down to architecture team. So the next team that we want to talk about is architecture. In the context of IC design, architecture means that we need to decide what are the things that we should be including in order to fulfill the requirements from the specifications. Okay, let's say right now we are targeting gamers, right? So gamers are looking for high performance. Probably the architecture team need to decide, right? This time, do we want to move on to 3 nanometer? Because TSMC currently there is like a few technology nodes. There is probably like 10, 7, 5, 3. So 3 currently is the most advanced one. It provides a lot more transistor at your base layer. That means give you more compute power, means higher performance, and also every single transistor is smaller. That also means that your power will be consumed lesser as well. So but the thing is it's more expensive, though you need the architecture team to decide whether our customer is willing to pay this kind of premium for the extra performance and also power saving For gamer, I think it's yes, right? Because gamer always looks for the best product. They want the fastest, they want the best, right? And so then the architecture could decide, all right, this time on, let's move on to 3 nanometer. And then after that, the architect also need to decide what kind of IP should we include. Like IP means intellectual property. Do we want to include AI engines? Because like recently we need to do Zoom call, then we need to blur all the background. All these are using the AI engines. Then do we need like DSP, your digital sounds processing? Do you need SerDes, serializer, deserializer? You need USB. Okay, you need every kind of different IPs to mix together so that they can form a system on a chip to perform the functionality that's required by the specification. Okay, so all these are defined by the architect. So this is the thing is very important for architect is to look through the vast area of items so that they can know what scope to put into the design. Okay, by controlling the scope is very important because if the scope is not being controlled well, if you just want to get everything under your portfolio, you want to get the very advanced complex design, everything to customers it sounds good, but for the project management it could be terrible because we have limited time, we have limited resources. If we put in too many stuff into this design, it will just cost too much resource to finish, or it might just cost too much time. Then at the end, if the project couldn't finish on time, it cannot deliver to the hands of the customer, then you might cause delay that will burn your money, that also will destroy your reputations. So it's very important for architect to know every single details of it so that when they put those things together, those things are feasible and able to be built in the designated time frame. Okay, and moving on to the context of designing a building, it is like the architect need to decide, okay, how do we design the exterior this time. Let's say we are designing a luxury building. Do we want to build 10 floor or do you want to build 40 floor? Definitely you want to build 40 floors, right? Do you expect to stay at 10 floor to look at a good view of the city or the sea view? No, right? You want to stay at a higher floor to look at a good view because you are standing at a very high up. Okay, so that's one thing. And also your exterior must looks extraordinary. You don't want to look like a normal place that you could see it everywhere. You want to looks very special, so your customer willing to pay a premium to stay there. Otherwise, if same as everyone, then why do I still need to pay a premium for that? Okay, so these are the things need to be decide, and also they need to decide, okay, whether if let's say this time we want to build condo, how many floor, the top floor we want to build penthouse or what, and then how many floor is designed for the high end condo, and how many of them is probably for the middle class like that. Okay, so these are the things that need to be decided, and all this specification, one it is complete sorry once all this architecture item is being completed, then we can give to the following teams, whereby it is called RTL design team. So in RTL design, in the context of designing IC, it means that we are using HDL code. HDL means for hardware descriptive language. So it is using either system Verilog or VHDL. Okay, the most common one right now is system Verilog. So using, if you don't know about HDL, you can go Google it. But HDL is used to describe the behavior of the hardware itself. Okay, let's say you want 1 plus 1 equal to 2. You can code the HDL in a way that it will do 1 plus 1. It will give you 2 as output. Okay, so all these are using code to explain the behavior, right? And the RTL designer also need to decide what kind of component that they want to use in the design. But they have probably like adder, subtractor, encoder, decoder, multiplexer, demultiplexer. Okay, they can just put this together, and then because like all these component can be coded individually, and then they can be combined to do different things together, and then so that it can perform at a system level. Okay, so that is why it's important for the RTL designer to describe the behavior so that it matches what is required in the specification. Okay, in the context of designing a building, it is like having a different space. For example, we have bedroom, we have kitchen, we have playground, we have car park, we have common area, probably like karaoke room, table tennis room, swimming pool. So all these are different part of your building. Okay, then every single designer, we call in IC design, we call RTL designer. Okay, every designer need to design their own space. Okay, there, but right now there's no physical information. Right now there probably is just to think, okay, let's say we say karaoke room, how big roughly do we want? Do we want to put how many sofa? Do you think how many people we want to fit? All these of little details. Okay, because just now specification is more on a macro scale. Okay, macro scale, it is like you want to decide the exterior of the building, everything. But right now when we go to the RTL design, it is more like you go into the micro scale, you go into kitchen, do you want to put oven and microwave, whether microwave is really needed, all this thing. Okay, everything is using written form to describe what kind of thing is required. Okay, so once this step is completed, then we will move on to RTL simulations. In the IC design context, you just want to make sure that you were saying that 1 plus 1 equal to 2, right? Your HDL is supposed to do that. Then I'm going to run a simulation to test whether your 1 plus 1 will come out as 2 or not. If it comes out as 3, then I'm going to feedback to the RTL designer to say, okay, this thing goes wrong. You need to recode this one so that it makes sure you can perform 1 plus 1 equal to 2. Okay, in the context of designing a building, the simulation probably is more like we want to make sure that your kitchen supposed to be able to have stove, you have oven, you have microwave. Then I'm going to check whether is your kitchen really able to cook all this stuff, or do you put bathtub in your kitchen, whether is it performing the correct functions. So I'm going to verify all these things before we propagate to the downstream, because once the upstream is wrong, it's going to make downstream works to be wrong as well. So we want to make sure nothing goes wrong at this stage. Okay, so that is for RTL simulations. After the RTL simulation is completed, then we're going to move to the next stage, that is called synthesis. During synthesis, in the IC design context, that means we going to translate the HDL code that is being done by the RTL designer. We're going to translate that into get level netlist. Okay, what is get level netlist? Get level netlist means that we going to use many different small component. Okay, the logic gates. We have AND gate, NOR gate, NAND gate, many different gate that you learn from your university. We need to combine them together, okay, and then so that it able to form the same function that is being described in the HDL code. All right, so the synthesis tool is a EDA tool, is a design automations tool. There is two coming from Synopsys, there's also two coming from Cadence. There are two different design automation provider. This tool is smart enough to understand your HDL code, and then it's going to translate all this thing into all these standard component, the logic gate itself. Okay, then all these logic gate are being connected in a way that is supposed to perform the correct functions. All right, in the context of designing a building, it is like you have many different space, right? Then right now you're going to put down different component into your design space. For example, you want to put windows, where you want to put your windows. Your window supposed to collect the best sunlight. You want to put your kitchen islands. You want to put many small items that is within your house, and then all this item is important to also form the same functionality as required by the specification. Okay, and then after the end of this stage, that is where you get your get level netlist. And in the context of designing a building, that is probably a list of items that you would need for your the real design, physical design like that, because you will say, okay, mention I need to how many sofa, I need how many doors, I need how many windows, all these things are being listed already. Okay, then after this we're going to proceed into the physical information implementations. Alright, then the next step is called place and route stage, and then this is a big stage that comprises of floor planning, placement, um, clock tree synthesis, and routing. Okay, then we move on to floor plan stage. For floor planning stage in the context of IC design, there is two main purposes. The first one is to provide a design area for your chip. Okay, and this design area normally is not defined by yourself, it defined by the higher level whereby the people would see the entire chip. Okay, let's say you are given like 100 micron to 100 micron, and then that is where your design area would be, and then you should place all your standard component within the area. You cannot place at other places. Right, and then the next thing that is supposed to do in floor plan stage is you need to build a power mesh. Power mesh is meant to distribute the power to your transistor that's as at the base layer, and then you need to deliver enough power to your transistor, otherwise your transistor will not able to sustain the voltage level. Okay, let's say 0 and 1. 0 is 0 volt, 1 is 0.8 volt. Then if your transistor doesn't get enough power, it's not able to sustain at 0.8 volt, probably it goes down to 0.5 volt, and that's where the unknown regions is. Then your chip will become malfunction because it don't understand whether this is a 0 or this is a 1, because that is the X region. So it's very important to design a robust power mesh so that your transistor able to get good power. In the context of designing a building, it is like you need to make sure that you need to have power distribution to every room of your entire house. Okay, you don't want to go to your kitchen and there is no power socket. Then how you going to boil your water? How you going to use your microwave? And if you come into your room, you want to make sure you're able to get the light on, you're able to use the computer, things like that. So all this power socket is very important. You don't have power socket, you don't get power, then it is just useless. Okay, so that is the main thing that we do in floor plan. Then moving on to placement. In the context of designing an IC, placement is important to place all the standard component within your design area. Okay, because we mentioned that there is a lot of combination logic gate. Probably there is more than 50,000, 100,000, or 1 million of this kind of gate. They need to be placed at the good location that is being optimized for performance, power, and area. So PPA is the three main criteria of designing a chip. So sometimes maybe you want higher performance, then probably you need to sacrifice power. Okay, so all these considerations is being done within the tool itself. So remember I mentioned about EDA, the design automation tool. So in the place and route, we also have another different tool that help us to do this kind of optimizations. It will take in the consideration of performance, power, and area, and do the best optimization possible. And as an engineer, what we do is we will guide the tool so that it will go and do the correct thing, because tool sometimes will still do something that is not supposed to do, and by providing input to the tool, we help the tool to perform better and do the correct job by itself. Okay, and all this logic gate is being placed at the base layer. Okay, so the base layer will be filled with a lot of transistor. Okay, in the context of designing a building, that means we need to put the standard component as well in the design area. Okay, let's say we are designing one condo, and then in a condo there is probably it's a 2-floor condo, and then we put the toilet. There's 4 toilet. Then do you want to put the 4 toilet, all 4 toilet at your second floor at the right corner? You don't want, right? Because you want toilet to actually separate into different floor and also different places so that it's able to be accessed at different level. And do you want your kitchen to be put at the second or third floor? You don't want, right? Because once you come back from grocery, you just want to go straight into your ground floor and put all your grocery on the kitchen island and put stuff into the fridge itself. You don't want to go to the highest floor and then put your stuff. It's just very time consuming and you are just wasting your power doing that. So same things goes to IC design. You don't want to place you want to place all those things that is need to be accessed by the I/O. I/O means input and output. If those things supposed to be accessed by the I/O, you want to put them near the boundary. Okay, you shouldn't put at the center of the design because it just take too much time to reach the center and also it takes power to reach to the center. Then you will just waste time and also waste your power, and that is not a good design. Alright, so it's very important to make an optimized placement so that for the downstream to able to perform as optimized as well. Okay, so we're going to move on to the next stage that is called clock tree synthesis, and in short form we call it CTS. CTS is called clock tree synthesis. In the IC design context, it is actually sending the clock to the entire design. Okay, so the receiving end would be the flip-flop. Flip-flop is a sequential cell. So if you don't know flip-flop, let me just give you a quick example and what it does. So remember I mentioned there is a bunch of combi logics that you will take in input and then you will go through the combi logics and then at the end you will have one single output that is either 1 or 0. And normally this 1 or 0 will be fit into the flip-flop because the flip-flop will help you to memorize this decision for a short period of time. Okay, once the clock comes in to trigger it, then it will forward this particular 1 or 0 to the output so that it propagate this signal to the next stage. So when the clock keep toggling, all these kinds of information will keep propagating and then the decisions will be sent to the next stage to process, and then the same thing happens over and over again. So there is ton of operation that's happening within 1 second. Okay, so that is the importance of having clock. If there's no clock, there's nothing triggering the flop itself to functions to propagate a signal, then basically that means your flop is dead. There will be no propagating signal, everything is just static. Okay, then in the context of designing a building, I just now was thinking what I can relate to this. So what came out of my mind is just recently there is a lot of people using smart home. Recently I mean like this 5 years, a lot of people start to put down a lot of smart home system, and I think probably because people are lazy. No, just kidding, not lazy. So I think smart home system is very important. It's because let's say you want to okay, after you off work, you want to come back to your house, you could customize your smart home system so that at 6:30 p.m. the air conditioners will turn on for you before you come back. Okay, so that when you arrive at your home, you have a nice temperature, you have a low temperature to enjoy a good environment. Okay, and probably when close to 11 you want to sleep, there's also a customized timer that dim the light so that you can go to a sleep mode, and then the next morning 6 o'clock the alarm is being set at 6 to wake you up, and probably at 6:15 your electric curtains start to open out slowly with a very smooth pace so that the little sunlight will come in by a little bit and wake you up very smoothly. And then by 7 there probably a automate coffee machine outside in your kitchens that help you to make a fresh coffee for you to enjoy your breakfast. So the key thing here is everything is clock. Okay, with clock then only the automations can come in. If there's no clock, how do you automate it? You don't know when it's going to happen. Okay, you need to go and turn on that manually when the times arrive, because there's no clock, everything is manual. Okay, so that is why clock is very important in the circuit itself. Every time when the clock toggles, it will trigger one operations. Imagine this clock is running like 3 gigahertz, 4 gigahertz in the CPU. Every single second, there will be more than millions of operations and decisions being made in the chip itself. So that's what made the CPU so powerful. Okay, so it is very important to build a clock that is evenly distributed to all your flops, so that it's able to meet the timing constraint that is being defined for the design itself. Okay, so that is the general introductions of clock tree synthesis. Moving on, we're going to routing. In the IC design context, routing means you are connecting the logic gates that is being placed in the design area to connect them together with a wired metal connection. Okay, they cannot be connected using Wi-Fi. Okay, they cannot just like transmit Wi-Fi to talk to each other. Okay, because they are just very tiny and are very close to each other. They are like even smaller than your hair. Okay, that's why they need to be connected using metal wire connections. There will be around 13 to 15 metal layer, so that for the wire to be routed from point A to point B, so because there are just many cells, there are probably more than 500,000 or 1 million cells that need to be connected to each other, so there will be many metal layer provided for them to do the routing. And all this routing also will be done in the EDA tool, and the EDA tool will do the optimizations to connect them together. And by routing them, they also cannot touch with another route because it will cause short. Alright, so there will be some sort of design rule that's given by the manufacturer. Let's say TSMC will give us a bunch of design rule that we need to fulfill when we do this kind of optimization, so that the route cannot be too close to each other as well, because we need to give some margin of error for fabrication. Let's say if the fabrication is error by 0.5%, then if we are too close by 0.5%, then they will cause short, and in the end our chip will fail. That's why we need to fulfill all this kind of design rule to make sure that when we send the design for fabrication, we are being manufactured in the best possible condition. Okay, and in the context of designing a building, the routing probably is more like you are putting down your gas pipeline. Okay, the gas pipeline probably is more relevant with the Western country because they need heating system, your water piping, your all your electrical connections to your light. Okay, so all these things need to be put down nicely, so that when you go to your kitchen, there is water for you to use and you can drink water. And also probably when you come back to your room when it is very cold, you can turn on the heating system so that you're able to sleep nicely. Okay, so all these are the routing, and once the routing has completed, then we will go to the next stage, that is called STA, PV, and also EMIR. STA stands for static time analysis. Is a method we use to analyze whether the design is able to meet the performance that is being defined by the specification. Let's say we say 3 GHz. So we are using STA to check, okay, whether this chip is able to fulfill that requirement. And then for PV means physical verifications. So remember just now I mentioned about routing, there is a bunch of design rule given by TSMC. So this physical verification is using all those design rule files to check against our layout. Layout means is our complete design with routing and also standard cell inside. We need to check whether the routing is fulfilling all these design rule. If it is, then we are good. Then lastly is the EMIR. EM stands for electron migrations, IR stands for IR drops. So EM is more like a reliability test, because like electron migration, it means that if you have a very long route, then when the currents keep flowing through for a very long period of time, let's say 2 3 years, whether this kind of current flow through the metal layer, whether this metal layer will broken down over time, whether it can sustain for maybe 5 years or not. So all these things will be measured. If there's EM issue, then probably we need to break the route to be shorter or what, or make the route to be bigger, something like that. Okay, that is more like a reliability test. And then for IR wise, like just now I mentioned, you need to deliver enough power to your transistor so that it able to sustain the voltage. So this IR drop is checking whether the voltage is able to sustain at the limited regions. Okay, let's say the limited region is 0.78 to 0.8. Once it's dropped below 0.78, then we need to fix the problem by probably adding more power mesh or lowering the drive strength of the cell so that it doesn't consume too much power. Okay, so that is what we do in the verification stage. So in the context of designing a building, um, this kind of stage probably is more like you need to verify whether your complete design view, all your house, your room, your bedroom, bathroom, everything is performing at the designated functions. Okay, all the things supposed to be in. Let's say we mentions we have stoves to cook. Do we really have those things being installed in the kitchens? Do we put it in the floor plan? Do we put it in the layout itself? If we are missing that, then probably we need to go back to tell the designer, okay, you missed this, then we need to put this in before we pass to the construction company to really build that building. Okay, so all these things need to be corrected before we release and out to the either it's fabrication company or it's a construction company. Okay, then once we complete all this stage, verification is all good, then we can go to the next stage that is called tap out. So the tap out in the IC design context, that means that we are handing off our design that is in the GDS format. GDS is a form of file. The GDS to the fabrication company. For MD case is TSMC, so we are handing off our design to TSMC so that they can fabricate. In the context of designing a building, that means they are handing off the design view probably to the contractor to help them to start doing the piling, doing building the entire building. Okay, so that is what it means by tap out. Once tap up is completed, and then that's where the fabrications happen. The fabrications company TSMC will start to build a chip, and then there is many different step in the fabrication step as well, but I'm not going to explain over here because that itself is already a very big topic. Today's I mostly cover about physical design domain. Alright, once the fabrication is completed, then the complete chip will comes back to Earth, and then we going to start doing the testing. Okay, because you've got the real chips ready, you need to make sure the real chips is also able to perform the same function as intended, because you're not sure whether the fabrication is being done correctly, whether there's any faulty fabrications that causes the things to be malfunction. So you need to test it whether the hardware that's being given is still doing the same thing that we expect it to do. Alright, so once we complete test everything, is if everything goes okay, goes good, then we're going to start to do packaging. We're going to put them, because the chip itself is like a very fragile thing. You need to make sure you package them and make them covered, and then there's heat sink so that it can distribute the heats nicely, otherwise it might just be overheat. So all this packaging are important. Once they're packaged nicely, then we only can sell to customer, then only we can start to do mass production and sell to the general public, or maybe the business partner of your company. Alright, so I think that is basically what we have today, and also I believe I covered the entire physical design flow. I hope that you're also able to understand the start to the end of the IC design flow. And if you have any questions, you can just comment down below. I will try my best to answer. So yep, that's all from me. I hope you learn a lot from this and also get a better clarity. Thank you.